Okay, let's dive into this. Welcome aboard. Today we're embarking on a high-stakes explainer, taking you deep into the heart of modern maritime engineering. We already know what ammonia is and how to handle it safely in theory. But now, we're looking at the very real physical auxiliary systems on board that allows ships to safely carry this highly volatile chemical and actually burn it as fuel. It's a delicate, deeply controlled dance down in the machinery space, and we're going to explore exactly how it all works.
To keep this intense chemical safely contained, we're going to take an intimate tour down below deck. Today we're looking at navigating ammonia at sea, followed by the ship's three crucial auxiliary systems: the gas detection system, the nitrogen generation system, and the water glycol system. Then we'll wrap up with a safer shipping future. Let's get started.
Section 1. The gas detection system, the senses of the ship. Think of this as the vessel's highly sensitive nervous system, designed to prioritize the safety of the crew above absolutely everything else.
Now, our primary goal is obviously to ensure that ammonia stays securely inside the tanks and pipes where it belongs. But we have to address that spine-tingling question. What if it leaks? When you're dealing with a chemical this potent out on the open water, there is zero room for error. The first and most vital line of defense is early detection.
The ship is essentially designed to constantly, quietly taste and smell the air. We've got these sampling tubes winding intricately throughout the machinery space and renewable cartridge-type sensors positioned right next to the vents, because those are the places where the chances of an ammonia leak are the highest. But we aren't just listening for ammonia. This system also keeps a really watchful eye out for a lack of oxygen, particularly in the areas where the nitrogen generators and bottles are kept. It's all about total, uncompromising safety. And this brilliantly illustrates the sheer scale of the safety measures at play here. There are over 50 of these standalone detectors spread across the ship, constantly sensing the environment, never sleeping. So, the crucial point is how this detection network reacts. If an alarm activates, the systems are programmed to act ruthlessly and automatically. They immediately trip, stop the flow of ammonia entirely, and instantly purge the compromised pipes with nitrogen. The ship protects itself first. Fault finding? Well, that intricate detective work is only done later, once the area is completely neutralized and safe. Section 2. The nitrogen generation system, the lungs of the ship. Now, what's really interesting about this slide is how we produce the heavy-breathing, high-pressure safety blanket that makes this whole operation possible. Let's break down this highly pressurized, intense process. First, the ship pulls in atmospheric air using a heavy screw compressor, squeezing it tight until it hits 10 bar. Then, we strip away the moisture, drying that compressed air down to a freezing -40°C dew point. From there, it's forced through restrictive filters and membranes until it reaches 99% nitrogen purity. Finally, that pure breath of nitrogen is fed into booster compressors, where it is squeezed to a staggering, immense pressure of 110 bar. That pure, high-pressure nitrogen is then carefully staged into a series of buffer systems. We have a low-pressure buffer tank that feeds those massive booster compressors, and once it's boosted to 110 bar, a medium-pressure line takes over, reducing and perfectly balancing the nitrogen to fill a 50 bar buffer tank.
Why these immense pressures, you ask? It all comes down to absolute control. These nitrogen pressures are meticulously calibrated for one incredibly seductive goal: to forcefully overcome the ammonia pressure and aggressively purge the danger the split second a fault is detected.
Section 3. The water glycol system, the bloodstream of the ship. Let's move to and see how this builds. If the nitrogen system is the lungs, this is the thermal bloodstream regulating the extreme, demanding temperatures of our liquid fuel. Water glycol is the perfect medium for transferring thermal energy, and the vessel divides this into two very distinct veins. The hot glycol system's job is to heat the liquid ammonia right before injection. When docked in port, it uses raw steam, but out at sea, it cleverly scavenges waste heat from the main engine jacket water. In sharp contrast, the cold glycol system is used to chill things down. It cools the ammonia gas in the condenser, the compressor itself, and the high-pressure pumps. And to achieve this icy precision, the cold glycol system relies on separate seawater pumps and dedicated plate coolers. Section 4. A safer shipping future, mastering the elements at sea. Navigating the high seas with volatile alternative fuels isn't just a concept anymore. It is a thrilling reality. And it's made entirely possible by understanding and mastering this complex, hidden machinery space architecture we've just explored. So I'll leave you with this thought. As we push further into the unknown waters of alternative energy, how will these hidden, high-pressure auxiliary systems continue to evolve to define the future of global green shipping? It's a fascinating engineering challenge, and I, for one, can't wait to see where it takes us next.